Hello everyone, welcome to SirPauTV. For today's video, we will be discussing finite approximations of area. Our knowledge in geometry focuses on the concept of areas, which is the amount of two-dimensional surface covered by a figure. We have familiarized back in high school different formulas for areas of different polygons such as squares, trapezoid, triangle, and others. But ancient mathematicians realized that it is quite more difficult to find the area of figures with curvatures involved. This area of figures with curvatures involved This area problem arises when we have a curve and we want to find the area of the region R below the curve. We can observe that the area is enclosed by the curve, the vertical line, x is equals to a and x is equals to b, and the x-axis, wherein our a is equals to 0 and our b is equals to 1. Unfortunately, there is no direct formula to use for us to simplify. How then can we find the area of R? Since we do not have yet the method of finding the exact area of R, we can do approximations by containing rectangles on the graph. Now, let us try to contain two rectangles in the graph. As we can see, we might observe that this is not the best approximations for the area. So each rectangle has a width of 0.5 and the height of, for this one we have 1 and for this one we have 0.75. How did we come up to that value? The 0.75 is from this function y is equals to 1 minus x squared. Having a value of 0.5, substituting it here, we can have 1 minus 0.5 squared, which is 0.25. 1 minus 0.25 is equals to the 3/4. So the area of the region R, we can say that it is equals to the area of the sum of all the rectangles, then subtracted by the pink areas. We can say that it is the summation of areas of rectangles minus areas of the pink region. So let us try to find the areas of the rectangles. So that is the length 1 times the width 1 plus the length 2 multiplied by the width 2. The areas of rectangles is equals to 1 multiplied by 0.5 plus 0.75 multiplied by 0.5. So the answer is 0.875. Now, let us try to consider 4 rectangles in the graph. So in the next figures, we can see that we reduce the width of each rectangle from 0.5, we go to 0.25. By following the same procedure and simply adding the total areas of rectangles, we can have a length 1 which is equals to, substituting the value of 0 to 1 minus x squared, we can have 1. Substituting 0.25 to 1 minus x squared, we can have 15 over 16. And substituting 0.5, we can have 3/4. And substituting the value of 0.75, we can have 7 over 16. Now finding the area of all the rectangles and then adding all rectangles, we can have the area for the rectangle 1 is 1 times 1/4. The area for second rectangle is 15 over 16 times 1/4. The area for the third is 3/4 times 1/4. And the area for the fourth is 7/16 times 1/4. Summing up all these 4 rectangles, we can have 25 over 32 or 0.78125. Now, comparing the two areas, we can say that our new area decreases in value. We can notice that this reduced value is taken from the pink areas. We can observe the area from the two, considering two rectangles, we can have pink areas which is as large as this one. So that the reduced area from 0.875 down to 0.78125, the reduced area is from the pink region. So therefore, we can say that in each of the sums that we computed, the interval AB for which the function f of x is defined was subdivided into n subintervals. So if we try many rectangles contained in the region R, we can see that the pink region, or now the blue region, is becoming smaller and smaller. Thus, it can suggest that having more rectangles contained in the region R and having a width of infinitesimally small, we can say that the many rectangles we contain, the more approximate value we can arrive, and we can get the exact value of the region R. So in that, we can say that the area of the region R is approximately equal to the area of the summations of rectangles, provided that the number of intervals will approach to infinity. So the many intervals we have, the many rectangles we can have also, and the more approximately we can arrive to the area of the region R. Thus, for the upper sum, in each of the sums that we computed, the interval a to b, over which the function f of x is defined, was subdivided into n intervals. So the value of the width is equals to b minus a divided by n. This width is then multiplied to the height. The height of each rectangle is x1, x2, x3, and x4, and so on and so forth. Substituting the value x1 to the function, we can have the height. And then multiplying the height to each width, now we can have the values of areas for each rectangles that we contain. So summing up these all rectangles, we can have the summation of all the rectangles. And if that interval approaches to infinity, we can therefore say that the area of the region R is approximately equal to the area of the rectangle, area of the summation of the rectangles as n approaches to infinity. That's all. Thank you. Goodbye.